This video is a supplement to section 4.5.3 in your text, which discusses muscle mechanics. I've added this supplement because the text talks a lot about models, and you'll need to develop a strong understanding of models as you move into your engineering careers, regardless of what type of engineering you do. So, a model is a tool that represents a simplified version of reality, a substitute for a real system. We often classify models into these three types: conceptual, physical, and mathematical. Leonardo da Vinci envisioned flying machines, and he sketched his idea model, or conceptual model, as a way to communicate his ideas to others, as well as to refine and develop them for himself. Next, physical models. We often use physical models to communicate and educate, but we might use them also to test a scale model, like this airplane in a wind tunnel. And finally, mathematical or computer models. In our digital age, we use computer models which are based on many equations. In the case of this image, probably the Navier-Stokes equation being calculated at every little grid cell for every time step. So many equations, many reiterations of the same mathematical equations. So now let's talk about ways to model muscle behavior. The mechanical model, based on springs and dashpots, probably started out as a conceptual model, as scientists sought to represent the viscoelastic response of muscle, looked at the viscoelastic literature, and then thought about applying it to muscles. Early investigators probably next put together a spring and dashpot physical system, that is a physical model, to play with their ideas, and then satisfied themselves that they could do a good job of representing viscoelastic response in muscles. Experimental models, for example, taking a frog muscle and applying an electric stimulus and then seeing if that could be reproduced with springs and dashpots, could well have been their next step. I'm sort of speculating here. We do know that their next step was to employ mathematical models, and in that case, first they represented symbolic or representative systems like springs and dashpots with equations, and then later we will see they represented physiological mechanisms with equations. A computer model will calculate the equations repeatedly. Those same mathematical model equations, now we put them in a computer. We calculate the equations repeatedly over many locations in space. And we can also have coupled equations. For example, you can couple the motion of a muscle as well as its heat generation, and then model how the heat is pulled away by increased blood circulation. If you don't understand the underlying mechanisms, or you don't have enough time to investigate them, you might make a simple model that goes from input to output based on experimental observations, ignoring what the causal mechanism is. That's called a black box model. If you don't want to black box your system, that means you want to represent the real system. And if you're paying attention to the underlying mechanisms, or in our case the underlying biology, you call your more accurate and more complicated model a mechanistic model. Represents mechanisms, so called mechanistic. Once you've decided to go for a mechanistic model, your next decision is whether your model will be a lumped element or a distributed element model. In some disciplines, these terms are called lumped parameter or distributed parameter models. Let's talk through these distinctions in the context of modeling muscle behavior. For a lumped parameter model, a few discrete entities approximate the behavior of a more complicated system. Some severe limitations of these can be obvious, and look at the discussion on page 173 in your text that talks about the limitations of the Hill model, for example, and its successors, because they were lumped models and also because they weren't very mechanistic. Instead of being based on how sarcomeres and muscle cells operate, they were based on springs and dashpots. With a distributed model, you represent all the mechanisms in space and time in great detail. This kind of model is much more feasible now that we have smaller, faster computers. So now let's look at the series of models you will read about in section 4.5.3. The earliest were the lumped models like that of Hill in the 1920s. Then in 1957, A.F. Huxley, and I quote from your text, devised the cross-bridge model based on structural and energetic assumptions. End quote. So this was a conceptual model or an idea model. He assumed how the cells must be functioning, these long, thin muscle cells. The word ultrastructural in this definition on this slide means that at the cellular level, it means that the scale is at the cellular level and even smaller at the myofibril level. Then, by the time we get to 2009, Palladino and Nordegraaf have developed a mechanistic, distributed computer model, which we will talk about in a couple of slides from now. And it's mechanistic because it's based on that sliding filament theory that was first proposed by Huxley in 1957, was corroborated by better understanding of the biology in subsequent years, and then was made into equations and finally a computer model in the years leading up to 2009. In the entertaining muscle structure and function video, the animation video, one of the most important ideas the author presented was the idea that the myosin heads were grabbing and moving along the actin, like climbing a rope, hand over hand. So this author represented the theory with an animation so that we could see the mechanism visually. People like Palladino and Nordegraaf model this mechanism of the cross-bridge bond with math. And the mathematical model that's described in your book uses one rate constant for attachment, that's the grabbing, and another rate constant for detachment. Rate constants, these have to do with time. So time is important here. When you read section 4.5.3 or read it again, look for discussion with the words that have the phrases transient responses, rate functions, and the word time varying. We all know that our muscles take time to exert forces, and that over time our muscles get tired, and our muscles can only do things so fast. So all this time discussion is very important for physiological systems, something that might not have been well represented by springs and dashpots. Okay, let's look now at how Palladino and Nordegraaf use a distributed model. We're still representing the math with dashpots and springs to portray it in this figure, but the model really contains Taylor series math type math in a computer program, and it represents the cross-bonding mechanisms. It represents sarcomeres. So the math is representing a lot of bonds. Remember, the bond is the little cross bridge formed by the myosin head, and a lot of sarcomeres, and with fast computers you can represent all this work going on at the same time at a bunch of locations. That's a distributed model, a lot of math allowing us to simulate biochemical actions occurring simultaneously in time and in space. Now let's take a deeper look at how this figure represents the math. Each bond is representing what we saw in the animation video. So the bond that I've circled in blue is representing that little animation of a myosin head forming a cross bridge or bond. We have M bonds in each sarcomere, and each sarcomere has two ends, and we have N sarcomeres. See the nth sarcomere circled in red. The blue circle indicates the first bond on the left end of the first sarcomere. The green circle is the mth bond at the other end of the same sarcomere. The orange circle is around the dot, 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 indicating that this is a series operation, that the computer is summing the effects of many of these sarcomeres distributed in space and in time. So once again, to summarize, we've taken a journey through these muscle models from the conceptual spring and dashpot lumped element model to probably some physical ones, and then conceptual based on the actual ultrastructural biology, And then finally, a mechanistic, distributed, mathematical, and computer model based on knowledge of the true ultrastructural function of the muscle cells. So here's the end of the story, the bottom line, to carry with you as you read through this section of the textbook and the rest of this chapter generally. 1. Distributed models are powerful. 2. Many disciplines use them to model complicated systems, whether it's groundwater flow models or flow of the flow field in a wind tunnel. Now, you can read the last bullet for yourself. So what we have here is that nature uses ATP, biochemistry, ultrastructural elements like myosin and actin, and life to make muscles move. How will the biomedical engineer reproduce that? Okay, this concludes this video, and thanks for your attention.